Right. Next, we will consider relays, opto isolators, and stepper motor interfacing with an AVR, which is chapter 14 in your books. Now, digital systems and microcontrollers or embedded systems, the current that they are driving are quite low. So if you look at the AVR fan out over here or on your data sheets, you will see that for 5 volts it sinks 20 milliamps and for 3 volts it sinks 10 milliamps current. Now, for low power application, this will be enough. But if you are going to drive something larger as a current wise from your I/O pins, we need some kind of drivers between the microcontroller and, let's say, the relays or the stepper motors. And there are two types of drivers that we can use over there. The one of them is the bipolar junction transistors, which we can amplify the current. We can increase the current with the bipolar transistors, but the problem is their thermal characteristics. So without a thermal solution, like a heatsink or a fan, the power bipolar transistors are very power limited. So you can find the different ICs on the market and you can use them, but you have to be careful. On the other hand, there's an alternative method which is known as Darlington. So Darlington transistors or Darlington pairs, which we have got as a Darlington drivers, and inside of those Darlington drivers we have got Darlington transistors. So Darlington pair is two transistors which is acting as a single transistor but with a much higher gain. So I can just draw the circuitry over here just for an info. I'm not going to go into the details. You can find more details on the circuits courses. So here we have got 5 volts and we have got the load. And that load is going to be driven by the Darlington transistors going down to another transistor, and that will be connected, and that's connected to the ground. So this is actually representing the Darlington transistor pair, which we are using in Darlington drivers. So Darlington drivers or Darlington pairs actually achieves very high current amplification by connecting two bipolar transistors in direct DC coupling. So the current amplified by the first transistor is amplified further by the second transistors, and it's just going to multiply the gain and increase the current drive for relays or maybe for the stepper motors. So that's why we prefer to use Darlington drivers if you want to connect something with the microcontroller and the high current devices. And we also have freewheeling diodes, which protects against the reverse currents of the inductive loads. These are the circuitries which we will need to connect relays, stepper motors or high current drives. Let's get into the relays and understand what actually they are doing. Relay is a electrically controllable switch which is widely used in industrial controls, automobiles and appliances, and it's actually allowing the isolation of two separate sections of a system with two different voltage sources. So for example, the 5 volt system can be isolated from 120 volt system by placing a relay between them. And this type of relays are called electromechanical relays. So a small amount of current and the voltage causes to switch a large amount of voltage and current. And electromechanical relays or EMRs, they have three components: the coil, the spring and the contacts. So relays can be normally open or normally closed types, and they might support multiple switches. So this is a different configuration of the electromechanical relays. We have got single pole, single throw, which is like a single switch. We have got SPDT, which is single pole, double throw. We can select from one of those switches. And there's a double pole, double throw, so double switches and double lines that we can select. So generally, spring is not shown, but it does exist internally in there. Normally, the relay has a minimum voltage below which the coil not to be energized, and this is called a pull-in voltage. Relay operation is shown in the figure. For example, we have got 12 volts on one side and 220 volts on the other side. Now, when we press the button, current flows through the coil. A magnetic field is created around this coil. So the coil is energized, which causes the armature to be attracted to the coil. And when the coil is energized, spring pulls the armature to its normal state of open or closed. So as I have mentioned at the beginning of this section, we need to have some kind of interface between relay and the microcontroller, which we generally use Darlington drivers. So ULN 2003 is the Darlington driver, which is available on the market, and we can place it in between the relay and the microcontroller. So if you want to turn on the lamp using a relay, the code is really simple, like we are setting the port to be a 1 or 0, like we are setting LED to be on and off. We just initialize the stack, then we set DDRB port B to be an output, and then we set the port B to be 1 with 0. Then we wait for 1 second, and then we clear the port B, so we are turning on and off, and it just carries on doing that. Contactors, they are similar to relays, but they're for a larger amount of currents. You cannot put them on a board. And we also have solid state relays. There is no coil inside of them. They don't have spring or mechanical contact switch. So it's made up of semiconductor materials. That's why we call them solid state relays. No mechanical parts. Their switching response time is much faster than electromechanical relays, and they have a greater life expectancies and low input current and small packaging. The next thing that we are going to see is a Opto isolator. So Opto isolator, as the name suggests, it's isolate two parts of the system. So for example, driving a motor. So motors can produce electromotive force, a high voltage spike produced by a sudden change of the current. Now, printed circuit boards, we can reduce the effect of this unwanted voltage spike by using a decoupling capacitors. But in a system that inductors, or let's say coil windings, motors, decoupling capacitors or diodes will not do the job. So in such cases, we use Opto isolators. So what is Opto isolator? It's like a circuit, something like this, which that's a LED input over there. So when current flows through the diode, it transmits a signal light across the gap, and the receiver produces the same signal with the same phase but a different current and amplitude. They are widely used in modems, modulator demodulators. And this is a diagram of it. So when you press the button over here, the current starts to flow and LED will start to blink, and it will send transmit the light across the gap, and the receiver produces the same signal with the same phase but a different current and amplitude. So that's what Opto isolator is. Now, if you want to control or interface the relays or any type of high voltage or high current equipments or the devices, we connect the AVR with the Opto isolator and with the Darlington transistors. So Opto isolator will help us to isolate the AVR so that we won't have any spikes. And we also have the Darlington drivers to drive a larger currents over here for the relays, and relay will turn on the valve. So digital side, which is the low power and the low current, and the analog side with the higher currents and the higher power. And also we have got Opto Isolator triac. So normal Opto Isolator is for only DC currents, but the triac version can also work with the AC currents. And that's the electrical circuitry inside of a chip. Right, so next we will consider the stepper motors. Now the stepper motors are actually translating electrical pulses into mechanical movements like with the other motors, but the speciality about the stepper motor is used for the position control. And we can give an example to, like, we can use them in robotics. They're used in dot matrix printers, the disk drives. So any kind of stepping controlled motors, we can use stepper motors. And you might ask, what's the difference between the conventional motor and the stepper motor? The conventional motors has got shafts which runs freely, but with the stepper motors, shafts moves in a fixed repeatable increments. So this allows us to move to more precise position, which we are going to see in details. So stepper motors generally have got a permanent rotor, which we call it shaft, so the center, north, south. Then around this shaft we have got stators. So these stators are normally named as A, B, C, and D, and they have windings. This is the most common way of implementing a stepper motor, and generally they have got 4 stator windings that they are paired with a center tapped common. So this actually looks like, so that's A, that's B, and the common center. Or we can have C and D and another common center. This is also known as a 4-phase or unipolar motor, and the center tap allows us to change of the current direction in each of the 2 coils when a winding is grounded, thereby resulting in a polarity change of the stator. Now from the slides I'll show you how it looks like in real life. As I already said, the difference between the conventional one and the stepper one moves in repeatable increments, which gives us more precise position. This repeatable fixed movement is possible as a result of basic magnetic theory that you might see in your physics course, where the poles of the same polarity repel and the opposite poles attract. The direction of the rotation is dictated by the stator poles. So the stator poles are determined by the current sent through the wire coils. And as the direction of the current is changed, the polarities also change, causing the reverse motion of the motor. Now, stepper motors has got 6 LEDs, and 4 of them representing the 4 stator windings that we have got around it, and 2 commons for the tapped LEDs. To operate the stepper motor, we apply a sequence of power to each of the stator windings, and then the stator rotor will rotate. These the sequences are generally given as a normal 4-step sequence, and these 4-step sequence are actually representing 1001, which is 9, 1100, which is 12, 6, and 3. Now, after 4 steps, same 2 windings is going to be on because 2 coils are energized at the same time. So as you can see, A and D, or A and B, or B and C, and C and D. 2 coils are energized at the same time, and after 4 steps, the same 2 windings will be on. So it's just going to repeat itself. For the sequences, We can start with any of the sequences in the table. We can start from step 1 or 2 or 3 or 4. But when we start with the sequence, we must continue the proper order. So we cannot jump from 4 to 1, or we cannot jump from 2 to 4 or 2 to 1. We have to go in an order. So if you're starting from 2, we have to go 3, 4, 1, 2, 3, 4, 1. Or if you're starting from 3, 4, 1, 2, 3, 4, 1, 2. That should be in the sequence. After completing every 4 steps, the rotor moves only 1 tooth pitch. So 4 steps equals 1 tooth pitch. You might ask how much movement is associated with a single step. So that totally depends on the internal construction of the motor, in particular the number of teeth on the stator and the rotor. So for example, if we have 200 steps per revolution, this will give us 200 divided by 4, 50 teeth. The step angle is the minimum degree of rotation associated with a single step. This means that the minimum step angle is always a function of the number of teeth on the rotor. And the steps per revolution is the total number of steps needed to rotate one complete rotation, or 360 degrees. So in other words, we can say that the smaller the step angle, the more teeth the rotator has. So the equations are given. The step angle is 90 over the number of teeth, and steps per revolution is 360 divided by step angle, or 4 times the number of teeth, and steps per second is given with rotation per minute, RPM, times steps per revolution divided by 60. Now I'll do an example about the calculation of these rotations and movements. So the example says, give the number of times the 4-step sequence must be applied to a stepper motor to make an 80-degree move. So we need to find 80 degree if the motor has a 2 degree of step angle. So step angle is given as 2 degrees. To find the number of teeth, this is going to be 90 over 2 degrees, as we just rearrange the equation, which will give us 45 teeth. And steps per revolution, SPR, it's going to be 360 divided by 2, 180 steps per revolution. The movement per 4-step sequence is going to be the 4 steps multiplied by the 2 degrees, which will be 8. Now, to move the rotor 80 degrees, as it says, as it's asking us, we just need to have 80 degrees divided by 8, which will give us 10 consecutive steps. So when it's asking the number of times the 4-step sequence must be applied to a stepper motor to make an 80-degree move, we just need 10 consecutive steps. Now you might ask a question that what happens if we want to move 45 degrees because the 2 steps are 2 degrees each? Once again, what happens if we want to move 45 degrees because the steps are 2 degrees each? The good thing about the stepper motors, they offer you to have an A-step switching, which we call it half stepping, and this provides a finer resolution, and you can have a 45 degrees as well. Now this slide shows us the stepper motor control with AVR. The common wires are connected to the positive side of the motor's power supply, so the 5 volts will be enough. And the 4 LEDs of the stator windings are controlled by the 4 bits of the AVR port, which is port B in this case. And we have to use a Darlington driver to energize the stator for high current drive. The sequence of code is given over here for us to show how it's going to rotate, and let's debug that code and analyze it. We start with stack initialization. Then the port B is going to be an output port, and it loads the step sequence 6. So step sequence 6 is actually step 3. Now step sequence 6 is loaded, which is 0, 1, 1, 0, and then it sends to the out port B. So we make the first step, then it performs logic shift right. So that means this is going to be, after LSR, it's going to be 0, 0, 1, 1. So the carry is going to be 0. Now if not carry, skip next. So carry is 0, that means we have to skip the ORI and we go back to jump L1 and we start again. Now this time we'll load R20, which is 0011, which is 3. In this case, this step 4. So this is step 3. This is step 4. And when we load that one, we perform another logical shift right. So this time, this is going to be 0, 0, 0, 1, and the carry is 1. And as this is 0, 0, 0, 1 and the carry is 1, that means the carry is set. So we have to perform the OR function, which is going to be ORed with 8, and this is going to give us 1, 0, 0, 1. Now that 1, 0, 0, 1 is our new value, and that has to be loaded to the motor drive. So it's going to be rotated to step 1. So now this is going to be step 1, and then we perform another logical shift right, which is going to be 0, 1, 0, 0, and the carry is 1. As carry is 1, we perform another OR function. So that's going to be 0, 0, 1, 1, and that will represent actually step 2. And then this will repeat itself as we are going in a continuous loop, and this will repeat the steps. So 3, 4, 1, 2, 3, 4, 1, 2. This is what we are going to get from this code. Now let's write a code example. A switch is connected to pin PA7. Write a program to monitor the status of the switch and perform the following. If switch is 0, stepper motor moves clockwise. If switch is 1, the stepper motor moves counterclockwise. We can start with init stack, assuming that we have got the stack and initialized it. Then we'll use port B again for driving the motor stators. LDI R20, it's going to be 0 hex FF. Port B as output. Then we send out DDRB R20. Then we have to make port A bit 7 to be an input. So clear bit, use DDRA 7 and make PA7 an input. Then we can start with the phase value LDI R20 0 hex 06 again, and we send it to port B R20. What we do, we start to check pin port A. So in R16 in A, we can use set R16 7. So T is equals pin A 7 with this statement. Then we can check the branch. T is set. Then jump to L1, let's say. And if that's not the case, we have to do logical shift right so we can rotate the clockwise. So LSR R20, then be orange if carry is not set, then we move to L2 or I R20 hex 80 or it. That means we have to L2, which is going to be call, need to have a delay and jump again. So we have to have again. So let's have to increase the indents so we'll be more organized. And we have to do L1 as well, which is logical shift left. So if not a logical shift right, it has to be left for the counterclockwise. R20, and repeat the same statements. Branch carry cleared R20, and then or I R20. But this time we have to OR it with 01. So we can say wait, repeat, shift left, if not carry, skip, then to do another call delay has to be L3, and that's going to be 3 R call delay and jump again. That's all we need to do. I'll just repeat. So we set the ports to be and port B to be an output and port A to be an input for the switch. First we set the first sequence as 6, and then we get the switch input. So if the input is set or reset 0 or 1, we make an action based on that. So if it's set, it has to move to over here. If it is reset, it has to be clockwise rotation, so logical shift right has to be done. And if not carry, we just skip, so we perform the OR function and then wait and jump again. And if the switch is 1, that means we have to make a clockwise rotation, and that comes from here. We do counterclockwise, so we shift the left and we OR with hex 1. Just repeats itself. So this is all you need to know about the stepper motor. If you have any question, please do not hesitate to ask me. Okay, so the last part of this lecture is DC motors. Now, DC motors, compared with the stepper motors, they're also doing the same job. I mean, they're translating the electrical pulses into mechanical movements. So this is their common functionality. Now, when we compare them with the stepper motors, DC motors have only positive and negative LEDs. So they don't have ABCDs. They just have positive and negative. And by connecting them to the DC source or DC voltage, it moves the motor to one direction. Either it's going to be a clockwise or anti-clockwise. And where we can find DC motors, we can find the DC motors in the motherboards, fans, or the drills that we are using at homes. So they are using DC motors. Now, with the stepper motors, we have seen that it moves in steps of 1 to 15 degrees, but the DC motor, it moves continuously. With the stepper motor, if we know the starting position, we can count the number of steps the motor has moved and we can calculate the final position. However, this is not the case with the DC motors. The maximum speed of a DC motor is indicated in rotation per minutes, RPMs. And the RPM can be reduced when moving a load and decreases as the load increases. So we will have a slower rotation as we have a bigger load. Now, there are a couple of important electrical characteristics about the DC motors. Like with the stepper motors, they have a high current and voltage ratings, and the nominal voltage can be from 1 to 150 volts depending on the motor. And as we increase the voltage, the rotation per minute will also increase. The current rating is the current consumption when nominal voltage is applied. There's no load, and this is around 25 milliamp to 5 amps. As we have already said, as the load increases, the rotation per minute is decreased unless the current or the voltage provided to the motor is increased, which in turn we are increasing the torque of the motor. And with a fixed voltage, as the load increases, the current or the power consumption of the DC motor is increased. And we have to be careful. If we overload the motor will stall. This can damage the motor due to heat that is generated by the higher current consumption. DC motors can be operated either as unidirectional or bidirectional. So with the unidirectional, we have got the motor and it's connected to the supply on both sides. Now we can have a clockwise rotation when we have connect the supply in positive and negative in this direction, or this is clockwise, or the counterclockwise. It's in a similar manner, but this time we are actually changing the direction of the supply. So the positive terminal is on the way around, and this will work in a counterclockwise. Now this is how a DC motor is operating. If we are considering the bidirectional rotations, we can achieve the bidirectional rotations by using relays or with a specially designed chips. And we can change the direction of the DC motor using those. So for example, we can consider H-bridge. Now the H-bridge looks like we have got switches on both sides. So this is switch 1, this is switch 2, switch 3, and switch 4. And we have got the motor at the center. How does this operate? Now the motor is not running because none of the switches are closed. So for clockwise, we need to turn on the switch 1 and the switch 4. Turn on switch 1 and switch 4. This means the current will start to go from the switch 1 and then to motor and then down to switch 4 and to the ground. So we are actually turning the motor clockwise rotation. For anti-clockwise or counterclockwise, this is going to be other way around. So we have to turn on switch 2 and switch 3. So this is going to be turned on and that's going to be turned on, and then we'll have the direction as follows, down to the ground, and that will be counterclockwise rotation. If all the switches are on at the same time, this is invalid. It will be a short circuit. So if you want to turn it on clockwise, we have to use switch 1 and switch 4. If you would want to turn on counterclockwise, we have to turn on switch 2 and switch 3 for this. We just connect the AVR with a driver transistor and the motor all together. This is what you can find inside of a fan package, so you're not going to have a separate microcontroller. Everything is there, you just need to supply the power to it. And more advanced version of that, actually we can use these Opto isolators to protect the AVR circuitry. We don't want to damage it. That's why we can use Opto isolator and Darlington transistor and the motor all together. So we have the digital power, the analog power separated with the Opto isolator. And as we already said, for the bidirectional control, we can use the H-bridge, as I already described on the board over here. So if you want to turn it on the clockwise, we have to turn the switch 1 and switch 4. So the current can flow from that direction to the clockwise version. Or if you want to have counterclockwise, the switch 2 and switch 3 has to be turned on so that we can have counterclockwise direction for the motor. And if both of the switches are turned on at the same time, then we have a short circuitry, so this is not valid, and we put the motor in an invalid state. So now let's do an example to see how we can interface AVR with the H bridge and the motor. So switch is connected to pin A. Write an assembly program to control an H bridge where the DC motor moves clockwise if PA7 is 0 and counterclockwise if PA7 is 1. Okay, so let's start with the ports. Now the ports are going to be we can use AVR's port B, and we can set the switches for each port B bit. That means, let's say SPI DDRB 0, so make PB 0 and out, which will be switch 1. Then SPI DDRB 1, make PB 0, PB1 and out, which is switch 2. SPI DDRB 2, make PB2 and out, which is switch 3. And SPI DDRB 3 and make PB3 and out, which will be switch 4. And we also need to identify the port A pin 7, or change put the direction. So clear bit DDRA 7, so that means we make PA7 and in, which is the switch that we need. Now we have to monitor that switch whenever it is changed. We have to do for 0 it's clockwise and counterclockwise if PA7 is 1. We have to check pin 7, so that means we can do SPIS pin A7, which means skip next if pin A7 is set. So we have to skip, so we can have our jump clockwise subroutine, which we'll do at clockwise if PA is 0. So if PA7 is 0, go to clockwise. So now we need to perform the counterclockwise switch ons and off. If I go back, so to have a counterclockwise, that means the switch 2 and switch 3 has to be on, switch 1 and switch 4 has to be off. In this case we can say CBI port B 0, which is switch 1, it has to be 0. SPI port B 1, switch 2 has to be on. SPI port B 2, switch 3 has to be 1, and switch 4, which is CBI port B3. So switch 4 has to be 0, off. And then we have to jump back, let's say L1 on in this case. So we need to go back to L1 to check the pin A7. Otherwise the clockwise routine, so it has to be SPI port B0, so switch 1 has to be on. Then CBI port B1, which is switch 2 has to be off, and switch 3 has to be off. Then switch 4 has to be on for for clockwise rotation. 1 and 4 has to be on. And in the end we have to jump back to L1 to monitor the pin. So that's all we need to write for H bridge driving the DC motor, and this is the configuration for it, and this is how we can interface it. Same solutions can be found on the slides as well. So we can use a different motor driver, which is L298N, and it can supply high current directly to motor, so we can actually separate the voltage between the AVR and the motor itself. We no longer need a switch drivers, Darlington drivers or the transistors, and we can just use this L298N. And alternatively, we can also use L293 or L293D. This is also a quadruple high current half H driver. So we can use two of them to have a two pair of full H driver, so that we can drive the motor. And all the details or the characteristic details are given in the datasheet. I'm not going to go into the details of that, but this is what we are going to have. Now, the next thing that we are going to consider is the pulse width modulation. So with the pulse width modulation, it's all related with the DC motors, but before we get into it, now the speed of the motor depends on three factors: the load, the voltage, and the current. So for a given load, we can maintain a steady speed by using a method called PWM. Now, by changing the modulating, the width of the pulse applied to the DC motor, we can either increase or decrease the amount of power provided to that motor, thereby increasing or decreasing the motor speed. And voltage has a fixed amplitude, but it has a variable duty cycle. And the wider the pulse we can have, the higher the speed of the motor. The microcontrollers with PWM circuitry embedded in, all we have to do is load the proper registers with the values of the high and low portions of the desired pulse, and the rest is taken care by the microcontroller. And this allows the microcontroller to do other things while PWM is running. Now, the ability to control the speed of the DC motor using PWM is one reason that the DC motors are often preferred compared to the AC motors. And because the AC motor speed is dictated by the AC frequency of the voltage applied to the motor, and the frequency is generally fixed, we cannot control the speed of the AC motor when load is increased. That's why we prefer to use DC motors with PWM function. To interface motor with the PWM function, we can use timer 0 or timer 2 and timer 1 or timer 3 in a similar manner. In the fast PWM, counter counts like it does in the normal mode. So after the timer is started, it starts to count up. Now, when it counts up until it reaches its limits, which is FF in 8-bit timer, it rolls over from FF to 0 and it sets high the timer overflow interrupt flag. Now with the fast PWM, this is what it's actually doing, and we can demonstrate this with a couple of figures. So for example, if I go further a little bit, in the timer 0 or timer 2 control register, we have got the VGM modes, which we can select fast PWM, which is 1-1, and we can use the compare match output mode. We can use 1-0 or 1-1, so clear OCN on compare match, non-inverting mode, or set OCN on compare match, which is the inverting mode. So I'm going to go into the details of this to show how we can use inverting or non-inverting modes. When both COM pins are 0-0, the OC0 pin operates as an I/O port. But when it is 1-0, that means the waveform generator, it actually clears the OC0 pin whenever the compare match occurs and sets it at top. If I draw the diagram of this, this is our ECNT0, and we have got FF and the output OC0. So we have got logic level 1, and this is of course time. So now we have got TCNT and OC0, and we start and go up to FF, down, up again, and down. Now what's going on with the non-inverted version? The waveform generator, I'm just repeating, clears the OC0 pin whenever compare match occurs. So we can have a compare match, let's say somewhere here, we set the value, okay, and whenever we reach there, we will get the value down somewhere there, and then it sets at top. So that's the second value that we are going to get, another compare match, and then another set at top. So how are we going to draw the OC output? Now start with logic 1, that goes down when OCR is reached, so compare match is occurred. So we cleared the OC0 pin, and then up to next, this is going to be 0. So when it reaches the top, it goes back to 1, a short amount of time, then we have another compare match, so it clears back again and stays 0 until it reaches the top, and then we set it again. So this is non-inverted operation for the PWM. We can also have a different values over there, and this can be extended, or I'm just going to demonstrate when it is both FF. So we can have both CNT0 and OC0. So OCR actually equals to FF, so it's the top value. So it reaches there, goes down, reaches there, goes down. So whenever it reaches the top, we have got to set it. And this is, in this case, it's always going to be 1, because duty cycle is going to be set it as F, so it's going to be straight line, so full power. So with the non-inverted PWMs, like we have demonstrated over here, the duty cycle of the generated wave increases when the value of the OCR0 increases. So somewhere here we have got lower duty cycle for this demonstration, but on this one, as we have got the OCR increased to FF, we have got the full power. We can also have an inverted version of this, where we need to configure the comp ports to be 1-1. Now in these cases, it is actually the inverted version of the above diagrams. So once again, if we have got FF, and this is all showing over here, and we have got an OCR value somewhere here. Now it goes up, down, up, down. Over time, we have got logic 1. With an inverted one, when it reaches to OCR value, it's actually going to be sets. So whenever the compare match occurs, this will go high, and it reaches the top, over here it will clear it, then the next OCR match will set it again, and for the next top we'll clear it again, so on. So it's totally the inverted version of what we have done on the above diagrams, as the name suggested. And if we have got the OCR value to be FFF, so it reaches over there, goes down, and reaches over there, goes down over time. That was logic 1. This is going to be, as it is inverted, it's going to be logic 0 in this case, because that's going to be cleared when there's a at the top of it. So this is how we can demonstrate inverted and non-inverted operation using fast PWM, and you can find different modes over here. So as you can see, TCNT values reaching to top, so OCR and update, and timer overflow interrupt flag set over here. And in these ones, OCRN interrupt flag is set. And based on that, either inverted or a non-inverted OCNs can be outputted. So in order to calculate the frequency of the waves or the duty cycles, there are a couple of formulas that we can use. So as we are reaching up to FFF, so we need to have 0 to FF, we need 256 clocks. And the OCR is somewhere in between that 0 and FF. Now that means the OCR is going to be OCR plus 1 for the pulse width, and then it goes up to FF, so that will represent the other side of the pulse, and then another OCR plus 1, and then pulse itself. So the timer clock divided by 256 will give us the frequency of that OC0 pin of this wave. And for the frequency of the timer clock can be found with the dividing the oscillator by the prescale factor. And the generated wave can be calculated as the oscillator divided by 256 by the prescale factor. And the duty cycles, if it's a non-inverting mode, it's just OCR plus 1 divided by 256 by 100. And if it's an inverting mode, it's going to be 55 minus OCR 0 divided by 256. And you don't need to memorize this, you just need to know that how are we getting these duty cycles based on the inverting or non-inverting modes. And there's a note over here which is important. 0% or 100% duty cycle can be achieved in inverted and non-inverted modes respectively, and in applications that require duty cycle between 0% to 100%, we need to avoid such settings. So I just want to do another calculation example just to demonstrate how are we going to find the values necessary or required. Generate a wave with duty cycle of 75%. So duty cycle with of 75%. Now the duty cycle 75% in non-inverted mode, we need to calculate the OCR 0. Non-inverting mode, we have got OCR plus 1. We know the duty cycle, so we just need to find OCR over there. So that means we need to rearrange the equation. Now 75 is equals OCR 0 plus 1 divided by 256 times 100. Now if we rearrange that, OCR 0 plus 1 is equals 75 times 256 divided by 100. And this will give us 192. That means OCR 0 will be 192 minus 1, 191. That we need to set the OCR value. This is how we can use these equations to calculate the OCR values, the duty cycles, or the frequency of the wave generated. As we carry on, in the fast PWM, as I already described, so OCR can be lower, and we will have in the non-inverting and inverting modes. So inverting modes, it clears, and when it reaches the top, it sets, and in the in non-inverting mode, it sets and clears at the top. So duty cycles and the frequency of the OC0 can be calculated based on the frequency of the clock and the prescaler and the 256, which is TCNT's highest value. Now the question says, assuming we have got a clock with an 8 MHz, make the pulse duty cycle 75% and frequency 31.250 kHz in non-inverted fast PWM mode. What do we know as a formula? Frequency of OC0 is going to be F clock divided by N256. Now this is going to be what? We know the frequency of the wave, which is 31.250 kHz, and we know the frequency of the clock, which is 8 MHz. We need to have is 256. So we can find the n, the prescale factor over there. N is going to be 8 megahertz divided by 31.250 kilohertz times 256, which is equivalent to 1. So that means that our prescale factor is 1. Now 75% duty cycle, that means 75 over 100, which will give us OCR0 plus 1 divided by 256. Now in this case, OCR0 plus 1 is going to be 192, as we already done in the previous example. So this is going to be 0 hex C0, and if you want to have OCR 0 itself, that's going to be 0 hex BF. And that's the value that we need to load for OCR 0. And we just need to configure the timer control register. So to configure the timer control register, that's going to be 0. GM00 has to be, if I go back over here, so it's fast PWM, so that needs to be 1. So COM N, which is going to be non-inverted, so non-inverting, it's going to be 1 0, so that will be 1, and that will be 0. So this is left us 0 1 1 0, which is 6. And then VGM1, it's going to be 1, because fast PWM, this is 1. And we have got the prescaler, so that's has to be 001, because there is no prescaling, as it is 1, and that will be 1001, which is 9. So that means we have to use 69 for the configuration of ECCR0 register. And if you look at the solution, OCR is going to be loaded with BF, and TCCR0 will be loaded with 69. So we can easily get that calculation done. Now, alternative to fast PWM, we also have phase correct PWM mode in the timers. In the phase correct PWM, this TC and T goes up and down like a yo-yo. So first it counts up until it reaches to the top value, so FF. Then it counts down until it reaches to 0. And the timer overflow flag is set when it reaches to 0. So I can show you this again with the PWM phase correct. So the VGM modes are changed to 1 0 now, and we still have the same non-inverting and inverting modes for the COM ports. And let's demonstrate that as well. So with the phase correct, we'll have, let's say, TC and T0, and that's FF. Can go up, down, and down. So counting up, counting down. It's not suddenly going to 0, it's counting down. So whenever it reaches to 0 over there, it sets the timer overflow flag B1, TOV0 to be 1. And this is what it does with the phase correct PWM. What I can say about that is when the COM is in the 00, it operates in the normal mode, so it's an IO port. But when it is 10, waveform generator clears the OC0 pin on compare match when counting up and sets compare match when counting down. And this is called the non-inverted phase correct PWM, which I'm going to show you with the diagram again. So you can have two diagrams. This is FF or TC and T0, and this is OC0, which is logic 1. And over time again, goes up and down like a triangle. So let's say we have got the OCR value somewhere here. So on the first one, it's actually going to clear. It's counting up, but when it's counting down, it will set it. Okay, so when counting up in the non-inverting mode, it will clears the OC0 pin. When counting down, it will set. So this is non-inverting. And with the inverting, CNT0 FF, so another triangle-like shape, OC0. So when we have got OCR somewhere here, when it is counting up, it will set. When it is counting down, it will clear. That's inverting. That's the only difference between them, and that's what we need to know actually. So we can play around with the COM ports if you want to set or clear, and this is how we can play around with them. And as I already said, it goes up and down like a yo-yo. So 0, 1, 2 up to FF, then down to FE, and so on to 0. And whenever it reaches to 0, it sets the flag, timer overflow flag. And similar calculations we have got for phase correct PWM. The only difference is in the normal fast PWM we have got 256, but in phase correct PWM I can show you from here, we go up to 55 and then we go down to 55. So in total, in one complete counting up and down, we have 510 clocks. So 2 times 255 it's actually doing. And OCR is set and cleared in between those. When you want to calculate the frequency of OC0, we have to divide by 510, or if you want to find the frequency of the generated wave. But with the duty cycles, it's OCR 0 over 255, because we can use the counting up or the counting down for the duty cycle. And for the inverting mode, it's 255 minus OCR 0. And that's the only difference between fast PWM and the phase correct PWM. And like we have done with the figures over here, this just shows how we are interpreting the inverting and non-inverting modes with the OCR values set or clears the signal on OC0. Yet another example which is similar to what we have done for the fast PWM. Now 8 MHz, the duty cycle is 75% again. The frequency is different, which is 15.686 Hz. Same formula, FOC0 equals EF clock divided by n times 510. 15.868 Hz will be equal to 8 MHz divided by n times 510. So n is going to be 8 divided by 15.868 Hz times 510, which will be equivalent to 1. And the duty cycle, or the OCR value based on the duty cycle, as we have got 75%, OCR 0 divided by 55, which is going to be equal to 191, the non-inverted version. So once again, and set that to be hex BF, and the TCCR 0, as we are going to use non-inverted phase correct PWM. So phase correct is 1 0, that means that's going to be 1, that's going to be 0, and comms is non-inverting, so it has to be 1 0. So this is going to be 6 again. This one is going to be 0 0 0, and there's the prescale 1, so it's going to be 0 1. So it will be 6 and 1 TCCR0 value. So in the end, we'll have the following code for TCCR0. and OCR 0. You might ask the question, what's the difference between phase correct PWM and the fast PWM? In fast PWM mode, phase of the wave shifts with different duty cycles, and we cannot achieve 0% duty cycle in the non-inverting mode or 100% in the inverting mode. But with the phase correct PWM, we can achieve 0 to 100% duty cycle without any problem. And for the motors, we generally use phase correct PWM modes. And the final example, it says write a program to monitor the status of the switch, perform the following. So if port A7 is 1, DC motor moves with 25% duty cycle at 245 Hz. If port A7 bit is 0, DC motor moves with 50% duty cycle pulse at 245 Hz. So AVR is connected to Opto isolator and the Darlington transistor and driving the motor. Now what we need to do, so for 25% duty cycle, that will give us 0.25 times 255, which is going to be 64. Now OCR 0 is going to be 64, and 50% cycle is 0.5 times 255, which is going to be 128. So OCR 0 is going to be 128. And if we have FOC 0 formula with F clock divided by N times 510, if we use phase correct PWM, then N is going to be F clock divided by FOC 0 times 510. In this case, N is 8 times 10 to the power 6 divided by 245 times 510, which will be equivalent to 64. And that's going to be our prescaler. Now all we need to do is to write a code for it. We start with DDRB, so port B3 is going to be an output. So we can say that SPI DDRB 3, and the port A is an active pull-up. Now we have to set the TCCR 0 value. So for TCCR, as it's going to be phase correct, and we know the prescale, and we can go back. Now VGM mode, phase correct, this is going to be 1, and COM1, COM0, we can have inverting or non-inverting. So let's use inverting mode. As it says, we can use the inverting mode. So that's going to be 1 1 1, which is 7, and then that will be 0, and it's going to be prescale 64, which is 100, so 100. Now that means LDI R16, it's going to be 0 hex 7 4, and out TCCR 0, it's going to be R16, and N is equals to 64. Phase correct PWM inverted. If you want, you can have a non-inverting, so you just need to change that to 10, which is going to be 6 rather than 7. Then check if the pin is set or cleared. So in A7, we can say skip. Next, if pin A7 is 0, so if it is 0, it's not 0, we have to load R16 with the value which is found 64 for 25 duty cycle. So I'll just wrote 64 for OCR, and SPIS, otherwise it will be pin A7 and skip. Next, if pin A7 is 1 or set, in this case LDI R16, it's going to be 128. So then out OCR 0 value on R16, and then we have to repeat that. We have to jump L1 where we monitor the pin. So that's all we need to do. What we have done, we set the active pull-up and the port B to be an output port. Then we have calculated the TCCR0 to be 7.4 if it's inverted, otherwise 6.4 if it's non-inverting, because we are using the prescaler and phase correct PWM. And we check the pin A. If it is 0, we skip the 64, so 25 per duty cycle. And if it is 1, we just set it to 128 for 50%. And that's all we need to do. So we talked about input capture, the waveform generation, the relays, the motor interfacing, stepper motors, DC motors, and we have seen DC motors control with PWM function. It was a combination of 3 chapters. I hope it is clear, and if you have any question, please note them down. You can ask me during the QA session, or you can contact me by email.